Hey class, Adam Ward here, continuing our treatment of long-term storage. In this video we're going to take a look at network turnover. So before you're ready to go down this road, you should have watched the prior video about channel water balance, where we calculated gross gains and gross losses. We'll need that information for this video. Alright, so network turnover. Let's look sort of conceptually at what network turnover is all about. And so I want you to picture this river flowing from top to bottom on your screen, with gaining water shown in green and lost water shown in red arrows. And I want you to envision that you're actually going to try to track these parcels of water. And so in this upstream reach, the water being lost most likely comes from the water that flowed in from the upstream end. And the water that's gained in green most likely flows out through the downstream end of this segment. And what we do in channel water turnover is sort of keep an accounting of this. So we have our orange water then flowing into the next segment. There's also green and blue water, and those losses are most likely some combination of blue and green, and most of that orange will persist on. And so you can imagine every time we move to the next segment, we use a different color to describe its inflows, and we try to keep track of how much water of which color is in which box. And the colors here are indicative of where in space that water entered the stream channel. So conceptually, this is an accounting problem. We just need to keep track of the gains and losses of water, and then at the end of every study reach, we can actually tell you, hey, this is where the water came from. This is how much of that blue water from the upstream end is likely to still be present, and this is how much of the orange water that just recently entered we think is present at any given point. So this is an image out of the Covino et al. 2011 paper. You'll note that in their paper and in subsequent work by Covino and others, they've assumed the end member of gain before loss that we looked at in channel water balance. In other words, these are the maximum volumes of inflows and outflows. And as you read through that publication, you'll notice that they use the notation Qij to represent the volumetric flow rate Q in reach I that entered from reach J. So what you're going to end up here is a large matrix of discharges, where you're actually tracking not just how much water is there, but how much water is there from every segment in the system. And I think the easiest thing to do here is to try to work through an example. These are not difficult calculations, but they do require some precision and some organization to keep track of what you're doing. And so let's envision that we know something about this study reach. We've gone to 3 segments, shown here as 3 boxes, and we've measured both the discharge in the channel, so 2 liters per second at the upstream end, for example, and we've also measured gross gains and gross losses. So here I'm showing you a gross gain of 0.1 and a gross loss of 0.2 liters per second. And so we could work our way down the system, and we could know how much water was in the channel and what the gross gains and losses were. The advance here from Covino et al. Is to start tracking where this water comes from, and if we can understand the spatial source or the composition of spatial sources of stream water at any given point. So let's try and walk through this with an example. In this first box, we had 2 liters per second flowing in, and we know that we had 0.2 liters per second of gross losses. So in that very first box, we'll assume all of those gross losses must have come from the water that flowed in, leaving 1.8 liters per second of that upstream water to flow out. Now, where does the rest of the water come from? Well, that's 0.1 liters per second from our gross gains. And we can check, do those 2 sources, the green and the blue, add up to the total? Yes, they do. We feel good about ourselves. So we have 1.9 liters per second flowing into the second box. All right, and just a quick erasure there so that you can see what flows into the second box is 0.1 liters per second of water that entered in reach 1, and 1.8 liters per second of water that entered somewhere upstream. Now, what happens within this box? Well, we know that there's 0.3 liters per second of gross losses. How should we apportion that between the 2 inflows? And so what we'll do is assume that water is lost in proportion to its presence in the channel. In other words, we'll take this 0.3 liters per second of gross loss, and what I'm doing in parentheses is asking what percent of this water came from our blue source. So that ultimately is 1.8 divided by 1.9. And so we'll apportion the loss there. We lose about 0.28 liters per second of water that originated from the blue arrow. And we can do a very similar calculation and find we lose about 0.02 liters per second of water that had that green origination. And so what we then learn is what are the losses, right? The gross losses, which we knew were 0.3 liters per second, we actually know it's not just 0.3 liters per second, but of that 0.3 liters per second, most of it was water that flowed through the upstream segment, or flowed into the upstream segment in blue, but a small fraction of it was that water that we had just previously gained. Now, from a water balance perspective, we then know if 1.8 liters per second of blue flowed in and 0.28 was lost to these gross losses, that leaves 1.52 liters per second of blue water, so to speak, that must flow on down the channel. And we can do that same calculation for water that originated in the upstream box. We find that 0.08 liters per second flows to the next. And lest we forget, those gross gains within that box, the 0.4 liters per second, those are also going to persist. And once again, we can double check if we add 0.08, 0.4, and 1.52, we should get 2 liters per second, the amount of flow we know is in the channel. Right? So what we're doing here is we're not changing our understanding of how much water is at any given point. What we're doing is saying, look, I want to keep track of these in some groupings. In the previous video, I used the analogy of your bank account and keeping track of transactions. Right? What you're sort of doing here is saying, I don't just want to know every transaction. I want to put all the transactions in order, and I want to perhaps group them by week. So let's do all of the first week, then the second week, then the third week, as we're going through here with the first, second, and third segments in our study reach. So it's a more detailed accounting of gains and losses and which water is flowing out or being lost, which water is being gained at any given point. Now, the exact same math can be done on the third box, and rather than write this out for you, I'll show you what my solutions were, and this is something that you all could work on to make sure you understand what we're doing. So of that 0.4 liters per second of red water that flowed in, if we think of it that way, water that came from segment 2, you can see I've got 0.36 liters per second flowing down the channel and 0.04 laterally. We can do the same division with the so-called green and blue water, and that lets us partition these out. Once again, we can double check that our Q loss value and our downstream value match up to the totals that we would have expected. So the idea here, again, just to drive it home, these numbers on the left-hand side in black, where it says totals, those are information that you would have from having done field studies or otherwise having a way to estimate gross gains and gross losses. This idea of network turnover begins with those data in hand. If I have gross gains and gross losses, then I can use them to work my way from up to downstream and tabulate the comings and goings of water with different spatial sources. So let me show you what this looks like in practice. So this is just a screenshot of the title page of the Covino et al. Paper. It's also linked in this module. And their work was done in this catchment up in Idaho. And what I want you to see is that they went out and did these channel water balance studies within 16 study reaches in their basin. And those spanned from just over 1 to under 1,000 liters per second. So they went out and collected enough field data that they could predict gross gains and gross losses everywhere within the study reach. So on the previous slide, or 2 slides ago, where I had numbers in black and said, hey, these are the total numbers. These are the total gains and losses. This is where those numbers would have come from in the Covino study, right? They did enough empirical work to build a regression that they were comfortable with. When you go through and add this up, not just for the 3 boxes, which is cumbersome, but for thousands upon thousands of segments within the study reach, you end up with a plot that looks something like this. So water flowing in closer to the upstream is in blue. Water that flowed in downstream segments is shown in red. The idea here is that at any given point, the thickness of that color band is telling you how much water entered at that location. And what I've highlighted here in orange, and you can see the orange arrow in the left-hand side, is an inflow from a tributary that is just downstream of point 3. And so we see this large vertical rise in the bar of colors right there associated with the color orange, right? The inflows to the segment. And so what you can see is, first of all, though that inflow created this large vertical band that's colored orange, because there's a lot of flow that came in from that tributary. So there's a very thick band. And as you progress in the downstream direction to the right in this image, that band gets smaller and smaller. And it continues to get smaller because that orange water is being is part of those gross losses, and it's being replaced with water entering from a local point with a different color, in this case with the reds. So the total height of this colored plot represents the flow at any given point, and then the color within it represents the composition of that water. So the spatial composition, where did that water come from? Let me just try to illustrate this with a quick doodle to help make sure you can really interpret this plot. So if we look at a bar graph, and we're going to pull discharge at points 2 and 4. So if we read where point 2 is on the left-hand panel, you can see that we're at a vertical location of about 60 liters per second. So there's 60 liters per second of flow in the stream. But the colors below it tell us where that water came from. So for example, we can see that there is a very thin bar that's comprised of very dark blue water, right? And that's water that originated at the very headwaters of the system, really within the first 500 feet. And then as the thickness of those bars continues to get lighter and lighter, what you're seeing is contributions from water that has flowed in since the upstream. So it has flowed in somewhere between 0 and this point. If we look over at point number 4, we can construct a really similar bar. The spatial origin of this water shows up as the color of those stacked bars. And so by the time we get to station 4, we see that there is a very small fraction of, I'm writing old in quotation marks here, the blue band is very thin. That means very little water is leaving the catchment that originated up in the headwaters. In contrast, most of the water that's leaving the catchment was within the downstream, the downstream 2,000 meters or so. So most of the water flowing out of this catchment did not originate up in the headwaters. Most of the water actually leaving originated close to the gauge. Very little water from the headwaters actually leaves. And we can tell that because that blue bar is so incredibly thin. So you can imagine that writing a clever script or algorithm here is going to be essential for your progress. It's a little cumbersome to work through even 3 segments, like I did a few slides ago and like I'll ask you to do in the learning activities associated with this video. So getting a sense of it with those hand calculations and then building yourself an algorithm or a program that can do this for you is definitely the way you want to go for a complicated system. And if you want to get to a plot like the one you're seeing here, you probably can't do enough empirical studies to cover this 6,000 meters of stream reach. You might even have to build those regressions to get at your gross gains and gross losses. Okay, so the goal in this video was for you to see how the gross gain and gross loss information that we've learned in our previous video can be extended to make predictions about where water comes and goes at the scale of river networks. All right, everybody, that's what I have to tell you about it. Check out the paper, and then you've got a learning activity to help you try this on your own. Thanks all.